Okay, let's dive in. If you're looking at the world of business AI agents
Mm.
and maybe wondering, okay, how do these things actually work? How do they learn?
Mm.
Then you're definitely in the right place.
hmm
Today, we're kind of cracking open the engine room, machine learning.
Yeah, the core of it, really.
We've got a stack of material here, notes, study guides, that lays out the absolute essentials, our
Yeah.
mission. Take these concepts, really understand what ML is, how the general process unfolds,
Smart.
and crucially, unpack why mastering these fundamentals is so key if you want to harness the power of AI agents in, your business.
Exactly.
Think of this as getting that high-level strategic picture, but without getting totally buried in the technical weeds or the code.
And what's really critical here, I think, is recognizing that machine learning is what lets these AI agents move beyond just simple automation.
Okay.
It gives them that intelligence to operate in complex, often unpredictable business environments. They learn from data to drive actual outcomes.
So let's start right there. The core idea. What is machine learning at its heart? I mean, based on the material. It's this powerful subset of AI, right? Where computer systems learn from data, they improve their performance over time on specific tasks, but without needing explicit programming for every single little scenario.
Precisely.
The analogy that really clicked for me from the notes was comparing it to a really seasoned business analyst.
Yeah, that's a good one.
They don't just follow a fixed flow chart. They look at years of market data, sales reports, customer feedback, whatever, and they learn the patterns, the trends, the subtle stuff, just through that experience with the data itself,
Uh-huh.
that ability to learn from experience from the data that's ML.
Exactly. And for business AI agents, that learning capability, it's the difference between having a rigid, static tool and having a dynamic, adaptable asset.
Right.
It's just indispensable because it allows these agents to operate effectively even when things are uncertain.
How so? Like what?
Well, they can personalize experiences on the fly. Think about an e-commerce agent recommending products that are genuinely relevant to you right now based on what it's learned.
Okay, got it.
Or they can discover hidden patterns in huge amounts of business data, maybe identifying niche customer segments you didn't even know existed, or spotting early warning signs of a market shift.
Ah, the discovery part.
And they adapt. A chatbot, for instance, can refine its understanding, its responses, based on the nuances it picks up from, millions of customer interactions over time.
So it gets better.
It gets better. This isn't just about processing data faster. It's about extracting real strategic value by enabling the agent to learn directly from the messy, ever-changing reality of business.
Okay, so that's the why. How does this learning process actually happen? The material lays out a general cycle that, when you look at it through a business lens, it makes a lot of sense, actually.
It does mirror strategy development.
Yeah, it kind of mirrors steps you might take in developing any complex business strategy or model.
Right.
So it typically starts with data collection. Pretty straightforward.
Yeah.
Gathering all the relevant info.
The raw material.
Exactly. If you're building an agent to predict sales, this isn't kind of like your sales teams, your CRM systems, just collecting every transaction detail, every interaction.
Oh, that input.
Then comes data preparation or pre-processing. And this seems absolutely crucial, maybe even more critical than the fancy algorithm you pick later.
Oh, definitely. Garbage in, garbage out.
Right. It's cleaning, organizing, transforming that raw data. Think of it like standardizing all those sales reports from different regions, handling missing values, maybe feature engineering, creating new, more useful bits of information from the raw data, like, I don't know, calculating average order value per customer.
Exactly. Improving the signal.
Because that garbage in, garbage out thing is a huge pitfall in ML, and it starts right here.
And actually, as part of that preparation phase, or maybe just before training, there's a really vital concept: splitting your data.
Splitting it.
Now, you typically divide it into 3 sets: training, validation, and testing.
Okay, why 3?
Well, think of it like preparing for a big exam or presentation. The training data is all your study material, your practice runs.
Okay.
The validation data is like showing a draft, maybe, to a trusted colleague. You get feedback, you refine it before the final version, you tune your approach based on this.
Makes sense. And the test set.
The testing data is the actual exam, or the live presentation to the board. It's data the model absolutely hasn't seen before during training or tuning.
Completely fresh.
Completely fresh. And why is this split so critical? It's mainly to avoid something called overfitting.
Overfitting,
Yeah.
meaning it just memorizes.
Exactly. You don't want your sales prediction model to just memorize the historical sales data so perfectly that it completely falls apart when it sees new sales figures it hasn't encountered. It needs to generalize.
Right. It needs to work in the real world.
Precisely. Testing on truly unseen data gives you a realistic measure of how well your model will actually perform out there, which is, essential for business reliability. You need to trust its predictions.
Okay, that makes a lot of sense. So once your data is prepped, it's split, then you move to model selection.
Choosing your tool.
You pick the right ML algorithm based on the specific problem you're trying to solve and the kind of data you have. Is it like linear regression, a decision tree, something else entirely?
Depends on the job.
Then comes the actual training. You feed that prepared training data to your chosen model, and you let the algorithm learn the patterns, the relationships within that data. This is where it builds its understanding.
The learning phase.
After training, you need to check how well it did. So you evaluate the model's performance, typically using that separate validation set you held back.
Right. How accurate is it?
Exactly. How accurate were its predictions? How well did it capture the pattern?
And often, it's not perfect first time.
No, probably not. So based on that evaluation, you might go back and do some parameter tuning.
The knobs and dials.
Yeah. Algorithms have these internal settings, hyperparameters, that aren't learned directly from the data, but they control how the model learns. Tuning these is like, I don't know, adjusting the fine controls on some complex machinery to optimize its output.
Playing the best performance.
Right.
Yeah.
And it's often iterative, right? You tweak, evaluate, tweak again, trying to squeeze out the best performance on your validation data, but being careful not to overfit to that validation data.
It's a balancing act.
Definitely. So finally, once you're satisfied, you move to prediction or inference.
Showtime.
Basically, you deploy the model, and it uses everything it learned to make predictions or decisions on new, unseen data out there in the real business environment, like forecasting next quarter's sales or identifying a potentially dodgy transaction as it happens.
And it's often a cycle, right? Because the world changes.
True.
So as new data comes in, you'll often need to retrain or update your model to make sure it stays relevant and accurate as the business environment evolves. It's not usually a one-and-done thing.
Good point. Okay, stepping back a bit, we've talked about the process. Now, the material highlights two fundamental umbrellas, sort of, that most of these learning algorithms fall under. And it depends on whether your data comes with the answers attached or not.
Supervised versus unsupervised.
Exactly. Let's start with supervised learning. This is built on labeled data. What does that mean? It means for each input example you give the model during training, you also provide the correct output, the label.
You're supervising the learning with correct answers.
Right, like teaching a kid to identify animals. You show them pictures and you say, this is a cat, this is a dog. You give the picture, the input, and the correct name, the label.
Got it.
The algorithm learns to map those inputs to the right outputs, so eventually it can predict the label for new pictures it hasn't seen before.
Makes sense. Learning by example.
Then you have unsupervised learning. And this, well, it works with unlabeled data. You give it inputs, but there are no predefined correct answers provided.
No teacher, no answer key.
Right. The algorithm just has to figure out the structure, the patterns, maybe groupings within the data all by itself.
Discovering structure.
Yeah. Using that kid analogy again, it's like giving the child a big pile of animal pictures and just asking them to sort them into groups without telling them the names first. They might naturally put all the cat pictures together and all the dog pictures together just based on visual similarities they notice. But they don't have the labels cat or dog to guide them. They find the groups themselves.
So the critical distinction really boils down to this. Supervised learning learns a map from input to a known output using labeled examples. Unsupervised learning explores the data to find inherent structure or hidden patterns without knowing the output beforehand.
And which one you use depends entirely on the business problem.
Absolutely. It depends on what you're trying to achieve and, importantly, what kind of data you actually have access to. Do you have labeled examples or just raw data?
Okay, let's really hone in on supervised learning for a minute because it seems like it's behind so many direct predictive tasks in business.
It really is. Very common.
So given you're predicting a specific outcome and you're using those labeled examples, the two main types seem to be classification and regression.
Correct. Two key flavors.
Let's take classification first. This is for predicting a categorical label, right? A discrete outcome. You're assigning an item or an instance to one of several predefined categories or classes.
Putting things in boxes.
Pretty much. And the material gives some fantastic business examples here, like spam detection. Is this email spam or not spam? 2 boxes.
Classic example.
Customer churn prediction. Is this customer likely to churn or unlikely? Fraud detection. Is this transaction legitimate or fraudulent?
Binary choices often, but not always.
Right? Like sentiment analysis. Is this customer review positive, negative, or maybe neutral? 3 or more boxes. Or loan application assessment. Approve or deny. Basically, you're sorting items into predefined buckets based on their characteristics. Some common algorithms here. Decision trees, maybe.
Yeah.
Support vector machines.
Those are common, yeah. Logistic regression, too, for binary classification.
Okay. Then the other main type of supervised learning is regression. This is different because you're predicting a continuous numerical value.
Not a category, but a number on a scale.
Exactly. You're predicting a number, not putting something into a finite category.
Like how much or how many.
Yes. And again, some powerful business use cases mentioned. Predicting the price of a house based on its features, square footage, location, etc.
Real estate staple.
Forecasting stock prices. Predicting the quantity of demand for a product next quarter. Estimating future sales revenue in dollars.
Crucial for planning.
Optimizing dynamic pricing. What's the optimal price point right now to maximize profit or volume? Or predicting customer lifetime value, CLV, as an actual dollar amount.
Very valuable metrics.
And a classic algorithm here is, well, linear regression, but there are many others too, right?
Many others, yeah. Gradient boosting machines, neural networks can do regression too, but linear regression is the foundational one.
Gotcha.
And for a business leader, look, understanding this distinction isn't just academic jargon, it's really practical.
How so?
Well, if you need your AI agent to decide whether to approve a loan application, yes or no, that's a classification problem.
Okay.
If you need it to set a specific price for a product or estimate next year's revenue figure, that's a regression problem.
All right. Different kinds of answers needed.
Exactly. Knowing which tool, which type of supervised learning applies to which specific business problem is really the first step in figuring out where you can leverage ML for tangible results.
Okay, clear. Now, switching gears to unsupervised learning. Remember, this is where there are no predefined labels.
Yeah.
So the AI agent acts more like an explorer.
Finding hidden patterns.
Right, finding hidden insights and structure in your data. The 2 key techniques highlighted seem to be clustering and dimensionality reduction.
2 major workhorses.
Let's look at clustering. This is about grouping similar data points together, based purely on their inherent features or characteristics. The algorithm finds the natural groupings that exist in the data.
It discovers the segments.
Yeah. In business, this sounds invaluable for, say, customer segmentation. Grouping customers into distinct personas based on their purchasing behavior, their demographics, whatever, so you can target marketing much more effectively.
Tailored messaging.
Or it's used in document categorization, maybe topic modeling, organizing huge collections of text. And a really crucial one, anomaly detection.
Spotting the odd ones out.
Exactly. You can identify unusual patterns, data points that just don't fit neatly into any cluster. And that's how you might flag potential fraudulent transactions that look different from normal ones, or network intrusions, or even manufacturing defects on a production line.
Finds the exceptions. K-means is a popular algorithm here.
Okay, K-means. Got it. The other big one mentioned is dimensionality reduction. This sounds a bit more abstract, maybe. It tackles complex data sets that have many, many variables or dimensions.
Lots of columns in your spreadsheet, basically.
Right. And it reduces the number of features, the number of columns, while trying its best to preserve the most important information.
Simplifying without losing the essence.
Why would you need to do that?
Well, sometimes dealing with hundreds or even thousands of features is just computationally really expensive, or maybe a lot of those features are redundant. They're telling you similar things. It adds noise.
Ah, okay. So in business.
You might use it to simplify the analysis of, say, hundreds of economic indicators down to just a few key factors that drive the market. Or for image compression reducing file size.
Practical.
Very. And in text analysis, like finding the core underlying topics across millions of customer reviews, simplifying a huge amount of text down to maybe 5 or 10 key themes. Principal component analysis, or PCA, is a common method for this.
PCA. Yeah.
Now, the strategic value of unsupervised learning, it often lies in discovery and efficiency.
Discovery.
Yeah, it helps uncover patterns or segments you didn't even hypothesize existed. Maybe find a completely unexpected customer group that needs a new strategy. That's discovery.
Okay, and efficiency.
And by simplifying complex data, making it lower dimensional, it can make subsequent analysis or even running supervised learning models on that reduced data much more manageable and sometimes even perform better.
Interesting.
The challenge, though, the big challenge with unsupervised learning is often interpreting what those discovered clusters or those reduced dimensions actually mean in a real business context. The so what factor.
Exactly. The algorithm finds the mathematical pattern. Humans, the business experts, still have to figure out the insight, the business implication.
Right. So, okay, we've covered quite a bit. The basic ML process, data splitting, the big difference between learning with answer supervised and learning without unsupervised, and how those break down into specific techniques like classification for categories, regression for numbers, clustering for groups, and dimensionality reduction for simplifying.
All driven by data.
All driven by data and all aimed at solving pretty distinct types of business problems. It really brings home how these techniques aren't just, abstract math in a textbook.
No, they're practical tools.
They are the building blocks for these AI agents that can predict outcomes, identify opportunities, streamline operations, all based on the data they encounter.
Precisely. And while supervised and unsupervised learning cover a huge range of problems, it's worth mentioning there's a third major paradigm. It's driving some of the most, cutting-edge AI agents today.
Oh, what's that?
Reinforcement learning. Reinforcement learning.
Mm.
Okay. The material gave us a little peek into this, and it sounded fundamentally different. The agent learns by doing.
That's the essence of it.
Yeah.
It interacts with an environment, think a game, a simulation, the real world, and it receives feedback. Rewards for good actions, penalties for bad ones.
The trial and error approach.
Exactly. The classic analogy is training a dog with treats or learning to play a video game. You try something. If it works towards your goal, you get a reward. The dog gets a treat, you score points in the game. If it doesn't work or it's detrimental, you get a penalty. No treat, you lose a life.
Okay.
And over many, many trials, the agent learns a sequence of actions, a policy, to maximize its total cumulative reward over time within that specific environment it's interacting with.
So the key difference here is it's not learning from a fixed, static data set, like in supervised or unsupervised.
Exactly. The learning is dynamic. It's about sequential decision-making in an environment that often changes based on the agent's own actions. My move affects the state of the game, which affects my next best move.
That sounds complex.
It is, and this makes reinforcement learning, or RL, uniquely suited for complex optimization problems where the agent has to make a whole series of interdependent decisions to reach a long-term goal.
Like what kind of problems?
Think about optimizing complex logistics routes in real time, where traffic conditions change, or training autonomous systems, robots learning to walk, self-driving cars navigating, even managing strategic investment portfolios, where each buy or sell decision impacts future possibilities and market reactions.
Wow, okay. So that's another whole area to explore later, maybe.
Definitely a deep topic in itself.
So, all right, as we wrap up this particular deep dive, we've journeyed through the core machine learning concepts powering so many business AI agents today.
The foundations.
We've seen that general process from data collection all the way to prediction. We've hopefully clarified that fundamental difference between learning from labeled data to predict specific outcomes that's supervised with classification and regression, and learning from unlabeled data to find hidden patterns or structure that's unsupervised with things like clustering and dimensionality reduction.
Finding groups and simplifying.
Yeah. And hopefully this helps clarify not just what these terms mean, but the types of business problems they actually help solve and the kind of strategic value they can unlock.
Yeah.
Really bridging that gap between a technical idea and the business bottom line.
Absolutely. And maybe building on this idea of AI agents that learn and adapt through ML, whether it's from data or through interaction, like with RL, maybe something for you, the listener, to consider is this.
Okay.
If the systems you deploy or the ones you work alongside are continuously changing their behavior based on new data and new experiences, how does that fundamental capability, that constant learning, require you to maybe rethink your own approach, your strategy, your oversight, maybe even how your own team learns and adapts within your organization? How does their learning change your game?